we will talk about limit of a function. We will be talking about the limit notion both graphically. So we will start with that. So we just start with seeing the graphs of comparing the graphs of 4 different functions, and then we will also talk about the limits by looking at the algebraic expression that defines these functions. Okay, so to get started, let me first write the notation. Let me first introduce you to the notation. So we will be talking about the limit of a function. So let's say we can have any type of function in here, and we will let the x values approach a number a. Okay, so this is similar to, sometimes this is equal to the function value f of a, but in general, what this means, so sometimes it might be equal to the function evaluated at a, but in general, what this notation means is that we would like to find the function values, the f of x values, when the input values, when x gets closer and closer to a specific value a. Okay, so let me show you on a graph in here first. Let's say this is the graph y equals f of x, and this is our point a, okay, on the x-axis. And as we get closer to a, so remember we kept picking intervals on Monday, and we determined the slope as we got closer to a point. So we will now formally define that, develop that idea. So today we are going to be defining the limit. That means we wonder, as x values get closer and closer to a, either from larger values or from smaller values, what happens to the function values? So let's say you pick this number on the x-axis, then the function value f of x equals this value. If you get closer to a, you pick another number, you find another value on the y-axis. You keep getting closer to a, and what happens to the y values? Are they getting closer to some value? So let's say this is the capital L value. So in this case, we can say that f of a, so the function value of a equals capital L, and we see that, let me change the color. If we pick a color, sorry, if we pick a x value that is greater than a, and we find it is y value, so we find this y value, and if we pick another value that is getting closer to a, then we find its y coordinate, its y value, getting closer to L. So in this case, we can say that the limit, so the y values are getting closer to a specific number L. So we can say that the limit of this function, as x values we pick are getting closer to a, equals capital L. Okay, so what is different between the first and the second sentence, second expression in here, is that the red one tells us at x equals a, the function value equals exactly L, but the second one tells us the function may not be defined at a, but at points very close to a, you could still say that the function values are getting very close to L. So in the second one, the f of a equals L, so this may not be true, but still you can say that when you are close to A, the function values will be close to L. So this is the difference. When you, in the first one, you know exactly at A, the function is defined and it equals capital L, the function value. But in the second one, you can say that you can, as you get close to A, the function values will be close to L. Okay, so once we see examples, the ones here, I hope it's going to be more clear, and then we will see other examples. So let's look at the first picture. Here, it may be difficult to read. This is f of x equals x plus 2. So this is the graph of the line y equals x plus 2. And we are interested in the values at 2. So when x equals 2, we are interested in the function values and the limits. So here is the function defined at 2. Can I get a yes or no? Is the function defined at 2 here in the first graph? Is the function defined at 2? Yes or no? Can I get an answer? So can we, yes, okay. Thank you, Megan. So at 2, we can say that f of 2 equals 4, right? So we can check the graph. So my writing pad is not working properly. I hope it's going to get better. Okay, so at 2, the function value is 4. Now let's talk about the limit, and then we will talk about its, we will learn its notation. So let's think about the limit as the x values get close to 2. However, we can get close to 2 from numbers, from values that are smaller than 2, or we can get close to 2 from numbers that are larger than 2. Now let's look at the first case. So let's consider we are picking x values. Okay, we are picking x values that are getting close to 2. So what happens to the function values? That means this is how we write it when the limit as x approaches 2 from the left side. So putting this minus means we are approaching to 2 from numbers that are getting close to 2 but that are smaller than 2, like 1.5, 1.9, 1.99, and so on. Okay, so we pick numbers that are smaller than 2, and this notation means the limits when you evaluate the function at those numbers, at those x values that are smaller than 2 but getting closer than 2 of the function f of x. So what can we say for the limit? So let's check the graph. So what happens to the y values as you are getting closer to, as the x values get closer to 2? What happens to the y values? Y values get closer to 4. Okay? So in fact, whenever the function is defined at a point, so here the function f of 2 is defined as 4, there is no problem, the limit also equals to that number. Okay, before we approach from the right side, from this side, let's look at the second example, and then we will come back to the first example. Now, consider the second example. In the second one, can we say f of 2 exists or not? So does f of 2 exist? Is it defined or not? In this example, is f of 2 defined? Does it exist or not? Yes. So what does this open circle mean then? What do you think? So can we say this open circle means that this point is not included in the graph? In fact, that means f of 2 is not defined. So in fact, in this function, f of 2 doesn't exist. I will just say does not exist. Okay, in short. Okay. Why? In fact, it is because the denominator has x minus 2. So we cannot define we cannot evaluate this function at 2. However, now let's consider numbers that are close to 2. Oops, sorry. Okay. Say that again. Okay. Sometimes the menu doesn't go away. Okay. So which one you wanna go over? So why doesn't f of 2 exist? So because we have an open dot here, right? That point is missing. So this function is not defined at 2. And why? Because the denominator in this function has x minus 2. And remember, we cannot divide by 0. So division by 0 is not defined. So yeah, okay, so we cannot divide by 0. And if you plug in 2 for this function, the denominator will be 0. That's why f of 2 is not defined. It does not exist. However, we can talk about the limit of this function. Okay, so we will talk about the limit of this function as x values get closer and closer to 2. Okay, and by putting this minus, what we mean is we are choosing numbers that are close to 2, but that are smaller than 2. Okay, so the limit of this function f of x as x values get close to 2, what do you think the limit would be? So when we pick, like the previous question, so for example, you pick this x value, which is close to 2, and this is the corresponding y value. You pick another x value that is close to 2, and you get another y value. Okay, you find the y coordinates. And we see that as we get close to 2, the y values close to what number here? So what is this number? What is this y coordinate? That's 4. Thank you. So in fact, we can, although the function is not defined at 2, we can talk about the nearby values. And we can still say that although f of 2 is not defined, because there is an open circle here, the numbers that are getting closer to 2, so the y value for the numbers that are getting close to 2 are getting close to 4. Okay, let me delete this and put 4 instead. So this is what is expressed with this equation with limits of this function when the x values are getting closer to 2 from smaller values equals 4. Although f of 2 is not defined, although it doesn't exist, we can still talk about the nearby values. Okay, so how about, now we said we would go back to the first example here, because we only talked about numbers that are smaller than 2, but getting closer to 2. So if you choose numbers that are larger than 2, but that are getting closer and closer to 2, that means we are approaching 2 from the right side, from numbers that are larger than 2. And let me show you how we write it. How do you think we should write it? Limits of this function f of x as x values approach to 2. So what do you think I should put on top? When we are approaching 2 from numbers that are, that's correct, that's a good guess, or I'll just put plus here. So if you are choosing numbers that are getting close to 2, but that are larger than 2, so, and you are checking what happens to their y values. So in fact, you are getting closer and closer, so you can see that the y values, where are they? Where are the y values getting close to? They are getting close to what number? 4. Thank you. So in this case, in the first example, when you get closer to 2 from right or left, in either case, the function values, the y values, get close to 4. So, okay, let me move this up a little bit. So what we can say is that so this is called the left limit, okay, when we approach a number from left side, and this is called the right limit. So these are one-sided limits. As you approach a specific x value, either from numbers that are smaller than that number, or either from numbers that are larger than that number. So if these both limits exist, and if they are equal, then we can say that the limit of this function as x approaches to 2, doesn't matter whether you approach from right or left, this will be equal to 4. So this is how we define the limit looking at graphically. Okay, looking at the graph, we checked what happens as we approach to x values. So we see that the y values of these points get close to 4. So we can say the limit of this function at 2 is 4. And the same thing applies for the second graph. When you choose x values that are larger than 2, so from the right side, but that are getting close to 2, what happens to their y values? So this is the image, like the y value, and this is the y value here. Where are they getting close to? They are still, again, getting close to 4. So how do we write it? Limit of this function as x values get close to 2 from the right side, from numbers that are to the right of 2, that are a little larger than 2, this still equals 4. So remember, in this case, the function is not defined at 2, but still the numbers, the nearby points are defined. So let's say 2.1, 1.99. If you are just around the point 2, you can still evaluate this function. You can't only evaluate at this point, but except this point, you can choose numbers that are very close, and when you evaluate the function, you will find that the y values are around 4. Okay. Now the third picture is slightly different. So in this case, we see that this is, do you remember what we call these types of functions? So the function, this is the expression. That's right, it's a linear function, but it has two pieces, and it is defined differently for numbers that are less than 2 and greater than 2. So this is an example of a piecewise function. Okay, have you heard of that name? No. Okay, so we will see we can see other examples, and so the only thing you should realize here is that there are two different lines here, right? So there are two types of functions. So one is this, and the other is this one. And in fact, so this is, let me just let's put the values. So here, this is y equals -1, so it passes through -1. And here it passes through 1. So this is the graph of y equals 1, right? So two separate graphs in this case. So this is number 2, and realize that if you pick an x value, so let's pick 2.5, 3, 3.5, anything we pick to the right of 2, what will be the function value? So what would you say for g of 3? For this function, when we plug in 3, looking at the graph, what should we find? So this is 3, and any number we pick, what is the y value for number 3, for example? What is the y value? 1. Thank you. So since this is a constant function, right? Any number you pick greater than 2, the output of this function will be positive 1, right? So 2.5, like 2.1, anything to the right of 2, the function value will be 1. How about g of 1? What do you think? What is the function value? What is the output when you plug in 1 to this function? Just check graphically. Is it 1? Okay. Or negative 1. So this is number 1. Okay, that's right. So when you plug in 1, we see that this point is on the graph. So when you plug in x equals 1, the y value should be negative. Okay, so let me clean this part a little bit again. Now let's think about the limits. Okay, well, before that, what do you think of f of 2? What is f of 2? Is it defined? Yes, piecewise means two different graphs. In fact, more precisely, it means we divide the interval, the number line, into different parts. So, and the function is defined differently in those two parts. So you could get two different graphs. That's right, because the function is defined differently into into different regions. So for this example, because we have the absolute value in the equation, x minus 2 will be positive. Sorry, I mean, when x is greater than 2, this will be positive, or when it is less than 2, it's going to be negative. That's why it changes. Let me read. If x of x equals 2, wouldn't be that it will be 0, and that's not defined. That's right. That's correct. So for this function, we should say that because we have 2, I mean, we have x minus 2, sorry, in the denominator. And when you plug in 2, you would get a 0 in the denominator. That's why we should say that f of 2 does not exist. Okay? So for this case, f of 2 does not exist. However, can we talk about the limit? Okay, the limit of this function. I will just keep it as g of x. Okay? So limit of g of x as x goes to, 2 from smaller values. So what does it mean? As x values approach to 2 from numbers, as x values, x takes values closer to 2 but less than 2. What would be the limit of this function? Okay, so we said that g of 1 is negative 1. G of 1.5, what is g of 1.5? It is still negative 1. So 1.75, let's say. Whatever number we pick from to the left of 2, can we say that the function value is always negative 1? Can we say that? Is that clear? Because we found, okay, because we found g of 1 was negative 1, and this is just a constant line, so anything to the left of 2 will give us the same y value, which is negative 1, so that we can say the limit of this function as x approaches to 2 from smaller values is negative 1. Okay, so we just check numbers that are getting close to 2, and all of their y coordinates are -1. Now, can you complete this mathematical sentence? So let's look at the green sentence. The limit of g of x as x values approach 2 from the right side. So what do we mean? We pick numbers that are getting close to 2, but that are larger than 2, right? That's perfect. That's equal to 1, okay? Why? Because any number we plug in, so just look at they are always equal to 1. So in this case, we have two different limits. Here we had the same limit, and we were able to say that this function has a limit at x as x goes to 2, which is 4. We said it here, and we can say it here. But for the third case, we should say that it does not work since it does not the same number, right? That's correct. So we should say that this limit does not exist. So, I mean, there is a break in the function. Okay, so in the third case, let me clean this graph so that you can see it better. Remember, the graph had a break. So whenever you have a break in here, so these are two different values. At number 2, so at x equals 2, there is a break. So the right limit and the left limit are different. Therefore, we cannot talk about a limit at this point. Okay, so we can talk about the left limit or right limit, but the limit itself does not exist because these two numbers do not match. They have to be equal to be able to talk about the limit. Okay, so there is one last case, and then we can discuss some other problems, but this is the main idea for today. Okay, what you should be understanding, like learning from today. So this is the last case. So now let's look at this one. So what happens in this case? Let's see first. Let's start again. If we can talk about f of 2, does it exist or not? What is f of 2? In fact, this is h. Sorry, let me call it h. What do you think h of 2 is? What should we say for h of 2? It does not exist. That's correct. Thank you. There is a minus 2. Oh, okay, in the denominator, right? That's correct. That's a good observation. So if you look at the expression, that there are two ways we can observe it. Either look at the expression, you can see that there is a 2 in the denominator, so the function is not defined at 2, or look at the graph. So there is no line, there is no point here which defines f of 2. So the graph doesn't exist at 2. So we can say that h of 2 does not exist. So what do you think the limit of the function h as x approaches 2 from smaller values equals? So let's think about this. Although the function value does not exist, so are the like in the previous cases, do we have some limits? So consider like 0.1, 0.1, 0.1, 1.2, 1.3, like 1.9. As we get closer to 2, what happens to the y values? What do you think they are getting closer to? So as you get closer to 2, what are the y values getting close to? Positive? Positive what? Positive infinity, that's right. That's correct. So what we see that this graph keeps increasing. In fact, it increases without a bound. So as you get closer to 2, the function values will grow very large. Okay, so this means we can say that this limit is positive infinity. Okay, you can, or I mean, just putting infinity would work. You don't need to put plus. So when it is just infinity, it means it is positive. And what happens if the x values? What happens if the x values get close to 2 again, but from values that are larger than 2? What happens to the y values? What happens to the function values? So, like, you can pick some numbers, and as you get closer to 2, what happens to the function values, like we had in the previous case? Can we say the same thing? Yes, we can. That's correct. So we can say that the function values go without a bound. So as you are getting close to 2, you will find very, very large numbers. Okay? So we can say that the limit of this function at 2, okay, so now let's change our color. So the limit, since the left, so this was, yes, the left limit and the right limit, they are both infinity. We can say that as the x values get close to 2, the function values go to infinity. So we can talk about the limit at 2. Okay, so in fact I will just complete this one too. Okay, so when we put a minus, when we put a minus, it means we are approaching from numbers that are less than a specific number. When we put a plus, that means we are approaching to a specific number from values that are larger than 2. And when we talk about the limits at a point, then we could either approach from left or right. So this exists when both of these limits exist. So in the last picture, in the last image, whenever the function values go to infinity, we talk about vertical asymptotes. So do you remember vertical asymptotes? Have you heard of that? Asymptotes, h of x, so the last function in this graph, we say that this function has a vertical, is the new word to you? Is the new term? Yes, it is new, okay. So we say that this function has a vertical asymptote. Yes, I'll just elaborate more on this. So it has a vertical asymptote at x equals 2. Well, that means this graph, okay, so when we graph this function, we should just put a dashed line at x equals 2, this vertical line. So this means the graph will get closer to this line, but it's not gonna touch it. Okay, so it just kind of shapes how this graph looks like. And it exists at places where there is 0. I mean, it exists on the places on x values which make the denominator 0, like this case. Okay, this is from the textbook. I just want to read this with you. Okay, so given a function f of x, I'll just pick yellow. So let f be a function defined at all values in an open interval containing a. So this means we have a function and it is defined. So let's say this is the value, the x value a, and this function is defined for all the nearby points on this interval. Okay, so this is what it means. It is defined on an open interval containing a. With the possible exception of a itself. So as we saw in the previous examples, the function may not be defined at a. You may have an open circle at a, right? And it says let L be a real number. If all values of the function f of x approach the real number L, as the values of x approach the number a, so as the values of x approach the number a, the function values, if they are approaching the number capital L, then we say that the limit of this function as x approaches a is capital L. Okay, so this is what we talked about, and this is symbolically we express this idea with this notation. Limit of this function when the x values get close to a is capital L. Okay, so we will see how we can, given a function, we can see how we can create a table of values and find, guess the limit, and then we can also see how we can guess it graphically, and in fact we will also talk about finding the limits given the algebraic expression. Okay, so let's where is that? Okay, so we talked about this. Now let's do an example where we estimate the limit of a function. So in this case, we are given an expression, and we said that we can either make a table of values, or we can draw the graph of this function. So this is the function we are looking for, right? And we will find the limit as x goes to 1. So is this function defined at 1? So if we let me call this function f. So f is the function 1 over x minus 1 divided by x minus 1. Okay, so you say that f of 1 does not exist. Why? Because there is x minus 1 in the denominator, right? I believe this is your reasoning. So the domain of this function does not include 1. F of 1 does not exist, but we can still talk about how does this function behaves, what are the values near 1, okay? So, what numbers should we choose? So, for example, if this is number 1, we can choose numbers that are larger, that's right, or that are smaller than 1. I would just the numbers we should choose should be between 0 and 2. Even you can start from 0.5. Well, you shouldn't start from 0. Just start as close as you can. So maybe we could consider this interval. So let's say when we plug in 0.5 for x, what do we find for f of x? Okay. So what we can do is, let me in fact write this function here. So 1 over x minus 1 over x minus 1. Let's simplify this a little bit, okay? So if we get common denominators in the numerator, what should we have? We should have 1 minus, so this is x over x, right? So get common denominators, we will have 1 minus x over x divided by, here we have x minus 1. So we are just simplifying this expression first. And how can we simplify this further? So realize that this is what we call a complex rational expression or complex fraction. So keep the top, which is above this fraction sign, so 1 minus x over x, and the denominator, take it, flip and multiply. So here this is x minus 1, you can put over 1. So we will flip and multiply by 1 over x minus 1. What did you do to get that? So what is the question exactly? I'm not sure. So I just took the function expression, right? And I just took this expression and copied it here, okay? And with common denominators in the numerator. So first I just copied the numerator. And for the denominator, so since the whole thing is divided by x minus 1, to be able to do division, I just changed this, like turned this to a fraction, so that we flipped and multiplied. Okay, makes sense. So there was no 1 here. I first put that 1, and then to be able to divide, keep, change, flip. That's right. Okay. So we did keep, change, flip. And okay, now we have these two multiplied. How can we simplify this? Can you think of a way? So this is 1 minus x. Well, okay. So if we factor out a negative 1 in the numerator, this becomes x minus 1. Okay, so just check the numerator. How you can, so you can say, if you factor out a negative 1, this will be negative 1 plus x. Okay, so let me just do it here. So when you factor out a negative 1, that's right, we will have negative 1 plus x. So when you factor out, divide both terms by negative 1, and you can change the order, negative 1 times, this equals x minus 1. Okay, so this thing equals negative 1 times x minus 1, and in the denominator we have x times x minus 1. Okay, let me repeat it. Well, this is a useful, okay, that part. So one thing, let me show you here. If you have x minus y and let's say y minus x, you can cancel these out. So one is simply negative 1 times the other. So if you didn't know this rule, so you can just double check yourselves. So here we had 1 minus x and x minus 1. So we were able to factor out a negative 1 and cancel them. So this function, in fact, simply becomes 1 over x. Okay? So this simply becomes 1 over x. Sorry. So you want to repeat the division part. Negative 1 over x, that's correct. Thanks for correcting. So this is negative 1 over x. Okay, so let me do the division part one more time again. So this was our original function, right? So this is our original function. So I just got common denominators in the numerator. So instead of 1, we can say this is x over x. Okay? So we have 1 minus x over x divided by x minus 1. Now, so there are two fraction bars. So this is the main fraction bar. So one fraction above and another expression under. So I just turned this into a fraction as well, so that we can divide these one. So keep the expression in the numerator and flip and multiply the denominator. So keep this, change this to the operation to a multiplication, and keep, change, flip. So flip the other one, which is times 1 over x minus 1. Okay, so when you multiply these, you will find negative 1 over x. Okay, so let me get rid of this part. So what did we do? We just simplified our function, right? So instead of evaluating this expression, we can evaluate the neater, the easier expression, which is negative 1 over x. So let's now use our calculator. So I will just open one in here. Okay, so the function is negative 1 over x, right? So I'm just going to be using like 1 over x function, and we can put a minus when we find the result. So our first x value we chose was 0.5. So 1 over 0.5 will be 2. Let me put it here. Oops. Okay, so now let's go back to our original question. So what are we trying to find? We are trying to find the limit of this function when x values get close to 1. So we started with this number. Oh, wait a minute, I forgot to put a negative 1. A negative. So it just simplified to negative 1 over x. So in fact, what we are finding is the limit of this function instead, because this just simplified to this function, as x goes to 1. Okay? Okay, so in fact, I'll just take it out of the way for now. So what we are doing is we are evaluating the limit of this function when x approaches, when x gets close to 1. So tell me another number that we should plug in to this function. Okay, so let's do it this way. Let's first choose numbers that are smaller than 1, but getting closer to 1. So what would you suggest? So yours is not a wrong suggestion. So choose a number which is less than 1. Okay, that's right. That would work. Okay, so x values are getting close to 1. So 0.8, I mean, we tried 0.5. Now we will try 0.8. And instead of plugging in the complex expression, we can just plug in here. Yes, please, you can ask your question.
So, Professor, I seen that you did it just keeping the x value. And can we just simply, now that we know the equation at the end, can we just simply plug in 0.8 now under negative 1 instead of doing the whole thing over again?
Yes, that's right. That's the purpose. I mean, that was the idea to simplify it. So we can use the simplified expression, this one. So we will divide 1 by 0.8. Okay, 1 by 0.8, right? And this is 1.25. Well, the thing is, these are both negative 1.25. We are dividing negative 1 by these numbers. So tell me another number which is close to 1. 0.9. So now let's find f of 0.9. Let me write it openly here, which is going to be negative 1 over 0.9. So we can just take this expression because we simplified it, and it equals to negative 0.9. Is it 1.111? Okay, so negative 1.1111. So let's get closer, 0.99. So 1 over 0.99, which is 1.010101. So when we plug in 0.99, f of 0.99 equals 1.010101, and so on. So what do you expect these values to approach to? You want to do another example, you want to try it with one other number, let's say 0.999. when you plug it into the function, what do you find? It's approaching to 1, right? So when you divide, well, in fact, this was also negative. So it's supposed to be negative. So 1, okay, let me clean it. 1 over 0.999 will give us 1.001001 and so on. Negative 1.001. Okay, so we can say, so we were trying to estimate this limit, and we can say the limit of this function, let me write the whole expression, the original expression, as x goes to 1 is negative 1. So this is what we would like to obtain eventually, and we made this guess by choosing numbers that were smaller but getting close to 1. Okay, so in fact I would just in fact we were a little quick to make this conclusion, so we were a little excited to do to conclude this equation. This is correct, but what we should do, what do you think we should also show? So far we only picked numbers that were smaller than 1, but in fact the complete solution to be able to say this limit exists and is equal to negative 1, to be able to say that we should also pick numbers that are larger than 1 and that are getting close to 1. So even if we don't complete this table completely, so tell me what numbers can we pick? So numbers higher than 1, that's right. Well, like closer to 1 will be better. Let's say we start 1.1, 1.01, 1.001, and we can check the pattern, what happens to the function values. Okay, so let's complete this table, maybe to see how it goes. It's not, it shouldn't take too much time. So 1 over 1.1. This is 0.909090. This is 0.909090. So if we find, and it was, by the way, it was negative, right? We always forget that. So if you divide 1 over, sorry, 1 divided by 1.01. So when we plug in 1.01, we find 0.99. Okay, 0.99. Well, in fact, when we simplified the function, we found this expression, negative 1 over x. So when we were plugging it into the calculator, so just for ease in calculation, I was just evaluating 1 over x in the calculator, and then, but the function itself has a negative. Okay, okay. So this was 99, and I mean, if you just keep checking, you will see that they also get closer to negative 1. So we can say that this limit, the limit of this function, is negative 1. Okay, any questions? So what we did, so we did part A, we picked x values that are close to 1, that are slightly larger or slightly smaller, and we checked the pattern as we get closer to, I mean, as the x values get closer and closer to the limit value, I mean the x value 1, the function values get closer and closer to negative 1. So then we can say the limit of this function at 1 is negative 1. Okay, so we showed in two directions, from smaller numbers or from larger numbers. In both ways, we can say, since both of them approach to negative 1, this limit is equal to negative 1. Okay, let's check it graphically. So checking it graphically is easier. Let's see it, but in fact it's a little tricky because, so let me show you the graphing calculator. So 1 over x minus 1, this was in our numerator, right? And what did we have in the denominator? So this was the original expression of the function that we were finding the limit at 1. Let me show you. So this is the expression that we were finding the limit at 1. So when you type it in a graphing calculator, and when you want to see the value at 1, wait a minute, where did we do wrong? So the value shows -2 here. 1 over x minus 1 over x minus 1. Wait a minute, negative. What? I don't know what happened here. Let me just give me a second. So the thing is, what I wanted to show first is that Desmos, at least this graphing calculator, doesn't tell us that this function is not defined at 1. So when you draw a graph, if there's some number that makes the denominator 0, you should put an open circle like the one in the picture, okay? But when you draw, if you draw this function, let me just draw this function in the Desmos graphing calculator. I mean, you can try it, and it doesn't show you that it is not defined at 4. Okay, so that's one thing you should be careful when using graphing calculators. It may not show you that this function is not defined at this point. Okay, so this is what happens in this case. At 1, it shows like a smooth curve in here. However, the function is not defined at 1. Okay, I think I think I saw where I typed wrong. So, okay, I just typed the function wrong. This is 1 over x minus 1 over x minus 1. So I just put 1, instead of 1, I just put x here. So let's fix it. Okay, now it shows correctly. So it shows us that, okay, so which is nice. So you see here, when we plug in 1, the function is undefined. So at least it tells us that this is the case, although it doesn't show this that the point 1 comma undefined. Let me see if it will mark it. No, it doesn't mark it. I would just put it like this. So 1 comma negative 1. Okay. So here the function is not defined, but we can say that the limit. So we can see graphically that the limit of this function, as x values get close to 1, is negative 1. Okay. Although this function is not defined at this point, you can still see that around the points around it, let's say 1.05, 1.03, the y values are getting close to negative 1. Is that clear? So is that why y is undefined? It is. So why y is undefined? Because we cannot plug in 1 to this function. So yes, when you want to plug in 1, it tells you that the function is not defined there, because it would cause a division by 0, right? It would cause a division by 0, so it tells you it is not defined. But I mean, I wish it would graph it, and here on the graph it just put an open circle, sorry, like this. So it would be nice if it showed you that there should be an open circle, because this is the correct graph. In the correct graph, you would have an open circle like here. Okay. Any questions? So let's move on. Okay, good. So so you will have on my open math, you will have some questions where you are asked to estimate the limits. So what you can do is you can just evaluate the function at nearby values like we did here, or you can just check graphically, just graph the function and see what is the limit. Okay, so for those questions. Okay, now let's talk about a little about infinite limits, and we will see another example, and we will probably be done after those. So I already mentioned to you that we can have a limit at infinity. So, and we said that we would have a vertical asymptote at those values, which make the denominator 0. So look at this function. Let me type this function. Let's call it f of x. So let this function f of x be equal to 1 over x. So let me show you how it looks when you graph it. So when you graph 1 over x, sorry, I will zoom out to see. So here is the function defined at 0. In fact, you can see it from the equation. So 0 makes, if you plug in 0 for x, the denominator will be 0. And you can see it graphically. So at 0, so in fact, as you are getting closer to 0, so as the x values 0.6, 0.5, 0.4, 0.3, so when the x values get closer to 0, what happens to the y values? The y values keep increasing, right? 0.1, 8.7. So they keep increasing, and so here we see that they are going to positive infinity. Okay. However, when you look at, that's right, when you look at numbers that are getting close to 0 from the left side, so numbers that are slightly less than 0, so negative 0.1, let me just move down, negative 0.098 and so on. So they keep going to negative infinity, so they keep decreasing. So we say that this graph has a vertical asymptote at x equals 0. So this blue line, you see the blue line? So this is the x equals 0 line, and this is a vertical asymptote for this function. So if you get closer, so for example at negative 15, sorry, in fact when you plug in x equals negative 0.067, the y value is negative 15. It keeps decreasing, negative 16 and so on. So the red curve, the graph of this function, gets closer and closer to the vertical asymptote, but in fact they never touch, okay? So they never intersect, although they are getting very close to each other. So this is the idea of vertical asymptote. We were asked to evaluate 3 limits. The limit of this function as x goes to 0 from the left, as x goes to 0 from the right, and the limit of this function as x goes to 0. So what do you think? So let's start. Oops. Let's start with limit as x approaches 0 from positive values, from the right side. So you can still make a table of values. Okay, so we already saw it graphically. Now let's consider it numerically, okay, with numbers. So when this is the number 0, you can choose 0.1. What is another number which is even closer? Can you tell me a number which is closer to 0? 0. That's right. 0.01, 0.001, and so on. Okay. Yes, exactly. So you can make the number as little as you like. And now what was our function? It was simply 1 over x. So let's find 1 over 0.1, which is 10. So when you plug in 0.1, f of 0.1 will be 1 over 0.1, which is 10. And if you plug in 0, 0, 1, what should you find? In fact, you will put one more 0, 100. Okay, so you just answered the next question. 0, 0, 1, you would have 1, 2, 3 zeros. This will be 1, 2, 3 zeros. Okay, so as you get closer to this value 0, the y values keep increasing. So we can say the limit, and they are all positive, so be careful with the sign. So this limit equals positive infinity. Okay, so we also saw it on the graph. As x values get closer to 0, the y values go to positive infinity. What do you tell for the, so we found this limit, okay, we found this limit. Now let's look at this one. What do you think the limit as x goes to 0 from negative values equals? If you, okay, negative infinity, that's correct. Sorry. So if you check the graph, you will see that when you get closer to 0 from negative numbers, from numbers that are to the left of 0, the function values go to negative infinity. Again, you would just choose negative 0.1, negative 0.01, and so on. Sorry. It is the exact same, that's right, it's the exact same but the negative. So you would find like negative 10, negative 100, negative 1000, and so on. So you would say that this limit is negative infinity. Now, let's look at the third limit. What do you say for this limit? Limit of this function as x goes to 0. What do you think we should say? So we found one-sided limits. So these are called, this is the right limit. Yes, so we found the left limit and the right limit. So remember, these are called one-sided limits. Yes. So Raja, that's correct. So these are one-sided limits, which means we are approaching the 0 either from right or from left. So when you approach from right, we found positive infinity. When we approach from left, we found negative infinity. However, since these are not equal, so these are different, okay, whenever the two limits are not equal, we say that this limit does not exist. We cannot talk about the limit of this function, okay? Any questions? So let's see one last example for this section, which is quite fun, I think, and we can just get started with the next section. So this is from the textbook. Let me tell you exactly what example this is. In fact, I put it here. Okay, example 2.1, 2.11, sorry. Okay, so this is in the textbook, and let's use the graph of f of x, which is in here. Let's use this graph to determine these values. Okay. Okay, so let's start with this first expression. So let's go one by one. Look at So what does it ask us? It is asking the limit of f of x. So this is the function f of x, okay, what we see here, the graph. And we would like to find the limit of this function as x approaches -4 from right or left, from the right side or left side. That's right. It's approaching from the left. And let's see. So here, the function is in fact defined at -4, right? So what do you think the left limit is? Okay, that's correct. So in fact, the limit as x values get closer to -4 from the left side. So just pick some values that are close to -4. What are their y values? Their y values are getting close to 0. Okay, so we can say the limit as x approaches -4 from the left side, so this limit equals 0. How about the limit as x values approach -4 from the right side? So if the function, if the x values approach to -4 from the right side, what do you think? So pick some value here, and it is y value is gonna become here, and just pick another value close to -4. The y value is here. Pick another number, y value is here. What are the y values approaching? So as the x's, that's right, as the x values get closer to -4, y values also approach to 0. Well, we can say this whenever we have a continuous function, which means we can just draw the function without moving our hands. And so the function is also defined at that point. So the limit will also be equal to the function value. So since the left and the right limits are both equal to 0, can we talk about the limit of this function at -4? And what should we say for the limit? What would you say for this? That's also 0. Okay, so the limit of this function at -4 is 0. Okay, so we checked at -4. And how about f of -4? We already answered this question. What is f of -4? The function is defined at -4, right? So the function is defined at -4, which is equal to 0. So part A, the answers to all the questions are 0. Okay. Or just change the color. Now let's look at the number x value -2. So x approaches -2 from the left. Okay, so good point. In fact, you answered this part. F of -2 does not exist. So let me write it. Okay, so this does not exist because there is a hole in here. However, if we approach -2 from numbers that are smaller than that, what are the y values? So just pick some number here. What are the y values approaching? So when you choose numbers, that's right, that are getting close to 2, the y values are approaching 3. Okay. How about the limit as x goes to 2, sorry, negative 2, from positive values. So if we are approaching, if the x values are approaching to negative 2, from values that are slightly larger than 2. What are the y values getting close to? Again, 3. That's correct. Again, 3. Well, this is going to be the case. So I mentioned you in the first case, whenever we have a continuous graph, whenever the function is defined at that point, we will have all these values equal. And if you have a function like this, that there's just a hole here, you can still talk about the limits from the right and limit from the left and realize that they are equal. So we can talk about the limit of this function, which is going to be equal to these numbers, which is 3. The only thing that is different is that the function does not exist only at this point. Yes, the number itself does not exist, but you can talk about the limits. Now let's see at negative 1. What happens at x equals negative 1? Okay, so this is the third case. We have discussed these cases in the beginning of this lecture. So at 1, so this is getting more exciting, more interesting. Well, let's maybe start with this question. What is f of 1? Is it DNE or is it defined, f of 1? Double check. Let's double check. So at 1, in fact, in this case, let's go up. I know it is not defined here. However, if you keep going up, what can you say? F of 1 equals 6. That's correct. So f of 1 equals 6. The function value 6 because it is defined here. Not in here, but here. So this is like a piecewise function. Okay, so it has different pieces. It breaks here. So there is a break in here, right? Okay, so we can say this is equal to 6, f of 1. So what would you say colored circle means? That's right. Colored filled circle means it is defined. Unfilled, like empty circle, means undefined. Okay, so as the so let's look at this limit. As x values approach to 1, as x values approach 1 from the left side. So just check a few points here. And what are their y values approach to? They are getting closer to 6 as well. Okay, so the limit of this function at x approaches 1 from the left side is 6. How about the limit as x approaches 1 from the right side? What do you think the limit as x approaches from the right side? So pick some numbers that are slightly larger than 1 and look at their y values. What are they getting close to? 3. Okay, so they get close to 3. So the limit as x approaches 1 from positive values from the right side will be 3. So does this limit exist? The limit as x approaches 1, it doesn't exist. So we should say this does not exist because these are not equal. 6 and 3 are not equal. So whenever there is a break in the function, so I'll just take it until here. So whenever there is a break, there is a jump, what we call a jump discontinuity. So in that case, we would have different limits on the right and on the left. So the limit does not exist. Okay, so we are getting there. I know you might be tired at this time, but you did great, and We are almost done. So let's look at the last case. Which color should we pick? Maybe this. What does the break mean again? So break, I mean, it is just the graph is, the two pieces are disconnected. They are not connected. So the graph doesn't go smoothly. So here there is a hole, and we call this like the hole discontinuity. And here the values jump from one value to another. So they are not connected. Okay. Well, there are two different functions that define here. Okay, no problem. Now let's look at -3. What is the behavior at at 3? So just read this question. Let's read it. We want to find the limit as x approaches 3 from the left values. Okay, let's see. So this is 3, and we would like to, we are approaching. Okay, so we are getting closer and closer to 3. What happens to the y values? So as you get closer, you see that the graph goes down. So the y values keep decreasing. -10, -100, -1000. So this limit, we should say, is -infinity. How did you write that, Megan? Okay, so how about the limit as x approaches the option key on a Mac? Okay. So as you approach 3 from the right side, what is the limit? So this piece, again, on the right side of 3, as the x values get closer to 3, the y values go to -infinity. Agree? So both as you get closer, as the x values get closer to 3, and you can see that the graph goes down, and we can say that there is a vertical asymptote at x equals 3. Whatever the function is, it must have a x minus 3 in the denominator, so it is not defined in here. The function is not defined in here. So what is this third limit? The limit of f of x. That's right, it's also -infinity, because these two are equal. In the previous case, these were not equal. So these are equal, these are equal. Whenever the two left and right limits are equal, the limit exists. Here they are not equal, the limit doesn't exist. So here we can still say that the limit exists and is equal to -infinity. And what do you say for f of 3, the last part? What do you say for this thing? For this guy? F of 3 equals what? What should we say for f of 3? DNE. Thank you, Michael. So this does not exist because the graph, doesn't show in here. So, right, as you see, there is no point on this vertical line. There is nothing. There is no intersection on the graph. Okay, so let me show you your assignment on my Open Math. So you should be ready to go. So the next section, in fact, I will just briefly get started, but we won't finish today. Is, I believe, this is more, this section was teaching the concept. So I hope you understood, you got the idea. So you will just need to find, for example, look at this graph and just find the limit at some of these points, and find the function value. So just like the problems we did. So the left limit, right limit, and the function value. So please practice while this is fresh in your minds. So these are graphical questions. And here you are asked to guess the value of this limit. And so you will find the limit as x goes to 0. It gives you what numbers to plug in. So you would just need to type this function and plug in, like evaluate at these points. Okay? So you will have different questions, but I mean the numbers, I'm just showing you the answer key for this question. So what you see in this case, so that we can discuss what's going on here, as x values approach 0, so you see 0.2, 0.1, and 0.00001. So when you evaluate this function, what is the limit? What do you guess? So it appears, based on these values, that the limit is negative 50. Okay, so you should just put, oh sorry, it was my bad. So you should just look at the numbers carefully. So negative 49.499, 49.499999. So as you get closer to 0, these values approach to negative 49.5. Okay. And another same type of question. You can plug in numbers, either like check numerically, and you can check it graphically, and either just type the limit or say it doesn't exist. Okay, so the nice thing now, we will in the next section we will see limit laws, and well, these will help us evaluate the limits without being have to plugging in numbers or checking graphically. By looking at the expression, we will be able to evaluate the limits. Okay, so this section is about the limit laws. So two basic limit results. Let's review from the textbook. So if a is any real number and c is another real number constant, so look at part I. So this expression tells us limit of x as x approaches to a equals a. So this is something trivial, right? Well, this is if you take x as the function, so f of x equals x itself. Let me just type it here. So if you take the function f of x, just the x function, and this expression tells us, so when you draw the graph of it, at any point a, this is defined, right? F of a will be itself, which is a. So because this is a polynomial, like a linear function, and we can say f of a equals a, so we can also say that the limit of x, limit of this function as x approaches a, also equals a. So this is one like basic rule about limits. And the second rule is telling about another basic result. And it is telling you if you have a constant function c, at any point a, the limit of this function will be c, because this is a constant function. Even you go from right or go from left, the function values will always be equal to c. So these are two basic limit results. So the limit laws tell us that if you have two functions, let's say, let me just introduce you from here. Oh, I don't know, my writing pad, since my son just played with it, it doesn't write properly. So, okay. So if we have two different functions, so the limit laws will tell us if you want to find the limit of these two, the sum of these two functions. So if you have a combination of functions, let's say it's addition, the laws tell us that we can find the limit of f, and we can find the limit of g, and we can add those limits. So this equals limit of the function f of x plus limit of the function g of x. So this is going to be a very useful rule, as let's say x goes to a, so you can just take x, take the limit at any point. So this theorem summarizes these rules, and we will see more examples next time. By the way, let me first go over this, and then we can just review next week's schedule, because there are some changes in the schedule. So sum law, which I just mentioned to you, tells us that if we want to find the limit of sum of two functions, then we can just find the limit of each function separately and add them. So if the limit of f is L and the limit of g is m, you can find the limit of their sum by adding L plus m. And similarly, if you have a difference of functions and if you want to find the limit at a point, you can evaluate the limits separately. So their limit, the limit of the difference, will be the difference of the limits. And same idea, when you multiply a function with a constant value, the limit of this expression will be equal to the constant times the limit of the function. So you can just do operations with limits. And if you have a product of two functions, if you multiply two functions, their limits will be the product of the limits of each individual function. Similarly for division. So the division of two functions, to find its limit, just find the individual limits and divide by take their ratio. And you can take a function to an exponent, so that you should take the limit to that exponent, or if you find some root of the function, you should to find its limit, you should take that root of that limit. Okay, so I will just show you one example, and then we will continue from there next time. So use the limit laws to evaluate this limit. Okay, so in this case, we are not plugging in numbers that are close to -3, right? So we are not checking it graphically, but we will simply apply these rules. So, sorry, let me just try again. So the limit of this expression, looking at the laws, we can say that, so we can say, let me just do this here, this is equal to limit of 4x plus limit of 2. So we can split this function, looking at the rules, to find this limit, as x goes to -3. And in the first case, so if there is a constant multiplied, we can just take it out. So this is equal to 4 times limit of x, as x goes to -3, plus limit of 2 as x goes to -3. Okay, so it doesn't work. What is this limit? We had said that this is just the function x, and we can in fact just plug it into the function. So we will say, since this function is defined at -3, this limit will be 4 times -3 plus, and this is the constant function. So these are the basic rules. So we just reduced the problem to apply the basic rules. So this will be simply plus 2, because this is constant. It's always 2. So when we do this evaluation, negative 12 plus 2 will be negative 10. That's right. Okay, so this will help us evaluate the limits. So we will work on this more. So that's it for today.